Hi friends, good morning. Welcome back to another session. Today we'll try to see problems on that is continuous strut. Let's see some of the things we have seen earlier. What are the cases? So if I go back, so today we'll try to solve problem on this case. Okay, earlier classes we have seen angles on same side of gusset plate and angles on either side of gusset plate. Okay, today we'll see problems on continuous, very easy. Okay, a double angle continuous strut of 3 meters long consists of two angles ISA 100 by 100 by 6 mm connected back to back on either side of gusset plate of 12 mm thickness. Find the design compressive strength. Find the design compressive strength of the strut. Okay, if the yield stress of steel as 250 MPa. So this is the question given. So it is connected to gusset plate on either side, and see, it is an equal angle. It is an equal angle section, means this is 100 and this one is also 100, and the thickness is how much? 6 mm. Okay, now the gusset plate thickness is what? 12 mm. Now if I write the properties for ISA 100 by 100 by 6 mm, the area is 1167 mm square, and see, if I take an angle, equal angle section, the centroid will be same, means CZZ, CYY, both will be same. Okay, so that CZZ equals to CYY, which is equals to what? 26.7 mm. So I will show you for equal angle sections. See here, for equal angle sections 100 by 100 by 6 mm, center of gravity CXXY CYY is how much? 26.7 mm, right? Now for this case, if I go back to our previous discussions, for this case continuous, effective length KLZ should be equals to KLY. You can take from 0.7 to 1 L. Okay, that is effective length of double angle continuous strut. Double angle continuous strut. Okay, that is KLZ will be equals to KLY, which can be taken from 0.7 to 1 L. So I will take 0.7 into what is the L given as 3 meters. So 2100 mm. Right? Next, coming to the radius of gyration. Now here see here once again, because of this being a built up section, a z axis, that is xx or zz, is same for single unit or combined, whereas y axis, it is y for whole section, and this y, this is for this section, and this is for this section, like that. Okay, so here with respect to z axis, rzz of built up will be same as that of, which is equals to rzz single angle, since being z axis same for the whole section. Right? Now from steel table, for the same 100 by 100 by 6 mm, 100 by 100 by 6 mm, it is how much? This one 100 by 100 by 6 mm, this is 30.9 mm, 30.9 mm. But RYY of built up will not be same as that of single angle, because see y axis for whole section is here, y axis for this one, so it will be varying. So under root of IYY of built up by area. Now you are supposed to calculate moment of inertia of built up section about which axis now? About YY axis. Okay, so about YY axis means what? See here, that is IYY of built up equals to, how many angles are there? 2 angles, 2 IYY of angle, okay, plus area multiplied by CYY plus half of gusset square, IG plus AH square. Now what is IYY about y axis? See here, 100 by 100 by 6 mm, the moment of inertia about, which one? IYY is 111.3 into 10 power 4 mm power 4 plus area already written as 1167 into CYY 26.7 plus half of the gusset plate thickness is given as 12 mm, half of it will be 6 square. Okay, if you solve this one, 26.7 plus 6 square into 1167 plus into 2, so how much you getting? So 1 second, 26.7 plus 6 square into 1167 plus 3 into e power 4 into 2. So always you have to write in terms of mm power 4. So 472.17 into 10 power 4 mm 4. Okay, so what is RYY? Under root of IYY of built up by area. So under root of IYY is how much? 472. Okay, 17 into 10 power 4 divided by area 1167. This is each angle into 2. So divided by 2 into 1167 root of. So you are getting how much? So 44.97 mm. Right? Next, now minimum radius of gyration from bow. Minimum radius of gyration from RZZ and RYY. So here this is 44.97 and this is 30.9. So that is equals to 30.9 mm. So 30.9 mm is the minimum radius of gyration. Now earlier we have discussed, that is deciding the buckling class of cross section. So deciding the buckling class of cross section as per table number 10 of IS 800 2007, page number 44, any angle section or built up section which comes under what? Buckling class C. Means you have to visit table number 9C. Okay. Now effective slenderness ratio. Effective slenderness ratio, that is KL by R minimum. What is KL? What is R minimum? 30.9. Okay. So 2100 divided by, it is 67.96. This is a ratio. Now you visit design compressive stress. Design compressive stress. Okay. Now for that design compressive stress, for KL by R value, this is 67, means it lies between 60 and 70. For a which one you are required? 67.96. Okay. So FCD values, I will try to provide 1 second. FCD values for I don't have that one. FCD values for this one is 168 and it is 152. Now we go for interpolation. For these values, please check table number 9C from your code book, page number 42. So 168, from here to here decrement, so minus of 168 minus 152 into 70 minus 60 into 67.96 minus 60. Okay. So 67.96 minus 60 into, okay, 168 minus 152 divided by 10, 168 minus answer. So how much you are getting? 155.264 Newton per mm square. Now I said you earlier that you have, this value should be in between these two, so you are obtaining. And the final one is what? Design strength. Area means what? 2 into 1167 into so 362 kilonewtons. Okay. Next we'll go for another problem, or we'll go for the directly design problem. So already in analysis we have done 4 problems, angle struts. Okay. Next we will go for design of angle struts. Okay. I hope design of angle struts. Okay, now we'll go, if we're going for design of angle struts, procedure steps we'll write here. What steps are involved in the designing of angle struts is, so first, suppose if factored load is given, for working load is given, factored load will equals to 1.5 into working load. Okay, after that, as I said, you design means you have to assume FCD. What is this FCD? Design compressive stress. Design compressive stress. Okay, right? How much you have to assume for single angle? Okay, you may take up to 90 Newton per mm square. For double angle, you may go for 150 Newton per mm square. Okay, after assuming this one, next, sectional area required. Sectional area required, that is AE equals to what? PU by this one, factored load PU by FCD value assumed. Okay, after that, select a suitable section from steel table based on area required. Okay, then what do you have to go? Based upon the, you have to calculate equivalent slenderness ratio for single angles, equivalent slenderness ratio, and equate it with what is this? Non-dimensional slenderness ratio. Okay, next, suppose this is for what? Single angle. Next, for double angle, same built up column procedure, means previous problem procedure is adopted. Okay, next, from table 9C. Why especially 9C? As I said, you any angle section or built up section, you have to visit table number 9C for required design compressive stress. This is assumed, this is actually what actually needed, FCD. Okay, next, you calculate PD. What is this PD? AE into FCD. What is actually called as design compressive strength. Okay, now finally, whatever the PD value you got, it should be greater than PU, this one. Then if it is, this condition arrived, then the design and strut is safe. Suppose if PD is less than PU, you have to revise the section. Okay, design a single angle strut to carry, okay, design a single angle strut to carry a compressive load of 150 kilonewtons. The center to center distance between end connections is 2 meters. Assume that connections are done by fillet welds. Okay, next, take yield stress of steel as 250 Newton per mm square. Okay, now here in the question not at all mentioned whether it is a factored load like that. So given data, this is working load. What is load? Working load. So working load is 150 kilonewtons. What about factored load? Factored load PU equals to 1.5 into 150. So it is 225 kilonewtons. Now effective length equals to L for, now how I am writing this one, effective length like this. Now we are assuming this condition. Okay, this condition we are assuming. Based upon that one I am taking KL equals to L, right? So, and here gusset fixity has been not given, you can mention, you can assume. Okay, assuming gusset fixity as fixed. So assuming the gusset fixity as fixed. Next, assuming, so this is a design problem. Definitely there is some requirement of assumption sum, right? Assuming FCD single angle, as I mentioned you, 90 Newton per mm square. Okay, now effective area required. Okay, effective area required. Effective area required is what? Okay, which is equals to PU by FCD. Okay, where A equals to what? PU 225 kilonewtons. If I multiply with this one, 10 power 3 newtons divided by FCD 90. Okay, so 225 into e power 3 divided by 90, you will be getting around 2500 mm square. Okay, so you have to choose a section. Okay, you have to choose a section from what? From steel table. That is, so anywhere it is not mentioned, anywhere it is not mentioned to whether to go for single angle or double angle. Okay, so for that what we do is we will choose a section that is from steel table. Okay, let I consider area. This one, see, 25 by 75 by ISA 150 by 75 by 12 mm with an area of 2562 mm square, right? So after choosing the section, the procedure will be same as that of you done in the analysis problem. I will attach the analysis problem what we done here, so that by looking that one you can solve this problem. Okay, please watch completely what procedure we are going to do. Okay, determine the design strength in compression. Determine the design strength in compression of a single angle discontinuous strut ISA 90 by 60 by 8 mm of length. Okay, 2.5 meters is connected to a gusset plate. Okay, through its longer leg by fillet welds. Take yield stress of steel as 300 MPa Newton per mm square, and modulus of elasticity, even though if it is not given, it is constant, that is 2 into 10 power 5 Newton per mm square. Okay, and assume the fixity condition, gusset fixity condition as hinged. Okay, now what is this continuous and discontinuous member? Okay, if it in a member edge to edge there are no separate suppose if you take a high tension wire towers, high tension towers, in that you will be having compression members which are discontinuous each other. Okay, like that particular compression member you will be having continuous. Suppose if I take a truss, okay, if I take a truss, okay, now here strut and here it is this is a principal rafter. Now for a principal rafter, this is completely principal rafter which is continuous with number of what? Supports. Whereas this is a strut, this is considered as a, whereas only edge to edge you will be having two supports and no other is there. That is nothing but what? Discontinuous, and this is continuous. Okay. Now we'll try to solve this problem. It is very easy, only formula based, it is somewhat difficult to see. Now here in this condition, hinged effective length equals to actual length equals to effective length, that is 2.5 meters or 2500. Gusset plate, longer leg connected, this is 90 and this is 60. Sorry, this one also should be like this. Okay, 8 mm. Okay, now what is the fixity condition? Hinged. So from table 12, page 48. Okay, fixity condition. Now we'll go for so see here, fixity condition, hinged. Okay, now what is a K1, K2, K3 values? K1 0.7, K2 0.6, K3 5. Okay, now right, next first we write the formula, then we'll come across lambda equals to under root of K1 plus K2 lambda VB square plus K3 lambda phi square. Okay, now already section is given 90 by 60 by 8 mm. Okay, for this you once visit SP6 chart. Okay, from that what you can obtain? Area, like that, right? So what is this? This is I section, means still if you go you will be getting channel. Next only what are those? Angle section. These are channel sections. Yes, angle sections. What are these? Equal angle. We require unequal angle. Unequal, I required yes, unequal angles. What is the size? 90 by 60 by 8 mm. 90 by 60 by 8 mm. Okay, now what is that 90 by 60 by 8 mm area? It is area equals to 1137 mm square. Now while calculating lambda VB, you want RVB, that is minimum radius of gyration. So here 90 by 60 by 8 mm. Now if I go for next page, see 90 by 60 by 8 mm, this line. Okay, second line. Actually this is a two-sided book. Okay, right. Here if you can see radius of gyration, RXX and RYY, RVV, this is RVV. Now how much it is? RVV 1.28 centimeters. I want in mm. So RVV, that is R minimum, is equals to 12.8 mm. If you can see these things, this is minimum, right? So still anything is required? No, Right. Now first we calculate epsilon equals to 250 by fy to the power of 1 by 2. What is 250 divided by fy is given as 300 divided by 1.2. Okay, so 250 divided by 300 to the power of 0.5. So how much you are getting? 0.912. Now everything is ready. Next we will calculate what? Lambda VV. First, what is the formula of lambda VV? Once we visit IS 800 2000 page number 48. Okay, 48, right. Now see here, what is the formula here? Actually this light is getting disturbed because of this brightness. L by RVV by pi square E by 250, and lambda phi equals to B1 plus B2 by 2t by under root of pi square E by 250. Okay, right. Now first we will try to solve this one. I will keep this aside. Okay, now what is this lambda VV? L 2500 divided by 12.8. L by RVV by, what is epsilon you got? 0.912 into under root of pi square into E 2 into 10 power 5 divided by 250. If I solve this one, pi square, okay, into 2 into e power 5 divided by 250. So denominator it is 81. 2500 divided by 12.8, it is numerator 195.31. Okay, divided by 81. So 2.41. This is lambda VV square. This is we calculated lambda VV square. Next, lambda phi. Lambda phi, which is equals to B1 90 plus B2 60 by 2 into 8 divided by epsilon 0.912 into root of pi square into 2 into 10 power 5 divided by 250. Okay, so see here in the denominator this one and this one, and C means this is 81. So B plus B1 plus B2, 90 plus 60 divided by 16. 2 into 8 is 16. So how much it is? 9.375. Okay, 9.375 divided by 81. So you get 0.115. So you got lambda VV here and a lambda phi, and you got everything K1, K2, K3. Substitute here. Therefore lambda E equals to, what is the formula? K1 plus K2 into lambda VV square plus K3 into lambda phi square. Okay, now if I substitute here, what is K1? 0.7 plus K2 0.6 into lambda VV you got as 2.41 square plus, what is K3? 5 into 0.115 square. Okay, so 0.6 into 2.41 square, 0.7 plus 3.48 plus 5 into 0.115 square, 0.066. Okay, now 0.7 plus 3.48 plus 0.066, root of answer. So how much you got? 2.06. Okay, this is lambda e. As per our procedure, now equating lambda e with non-dimensional effective slenderness ratio. Non-dimensional effective slenderness ratio. Okay, that is what? Lambda equals to Fi into KL by R square by pi square E with whole root. Now that is, we are supposed to equate like this. Now what is lambda E value? 2.06 equals to under root of, I know 300, Fi as 300. Okay, KL by R square by pi square into, okay, 2 into 10 power 5, right? So before solving, we'll do it squaring on both sides. Okay, what we do? Squaring on both sides. Now while doing squaring on both sides, what happens? This 2.06 square equals to 300 into KL by R square by pi square E, you remain with. Okay, now in that KL by R square equals to, okay, 2.06 square into pi square into what is E? This cross multiplication, 2 into 10 power 5 divided by 300. Okay, now if I substitute KL by R square equals to what you will get? 2.06 square into pi square into 2 into e power 5 divided by 300. You got 27921.76. Okay, now KL by R equals to, okay, root of 27921.76, which is 167.0. What? This is KL by R. Once again you see this step, we got the conditions. Based upon the conditions, we got K, K1, K2, K3 values from table number 12. Okay, from that you got 90 by 60 by 8 mm. You calculated, taken the area and minimum radius of gyration from the steel table. These two values are from steel table or SP6 chart. Okay, and we have elaborated the formula, and we calculated epsilon, and we calculated lambda VB and lambda phi values. Substituting here, you got lambda E, equivalent slenderness ratio value. So after getting this one, now we have equated that with non-dimensional slenderness ratio as per this formula. This is page number 33 of IAS 800/2007. Okay, after solving everything, okay, after solving everything, you got equivalent slenderness ratio 167. Okay, next, now from previous page we got KL by R as 167. Now deciding the buckling class, what we decide, that is from table 10, page number 44, Okay, any angle section, any angle comes under buckling class C. So design compressive stress, design compressive stress FCD can be calculated from table number 9C. Okay, now FCD from table number 9 means for KL by R and FCD for particular FI as 300 MPa. What is KL? You got 167, means it lies between 160 and 170. So here right, this is see, this is table number 10. In that, what this is angle section. Okay, so angle section, it comes under what? Buckling class C, right? So from table number 9C and particular 300 F yield stress, and it lies between 160 and 170, means for 160 this is 54.8 and it is 49.3. These two values for 300, this one, see, 160 and 170, right? So we'll do interpolation. 54.8, from here to it is decreasing, so minus of 54.8 minus 49.3 divided by 170 minus 160 into, we have taken first as this reference, so 167 minus 160. Okay, so 54.8 minus 49.3 divided by 10 into 167 minus 160. Okay, so 54.8 minus of answer, so you got 50.95 Newton per mm square, right? Now design compressive strength, okay, which is PD equals to AE into FCD. Okay, so what is AE? From what? 1137 mm square, that is 1137 mm square into FCD you arrived as 50.95. okay, so 1137 into 50.95. okay, so how much you are getting? 57,930.15 newtons or 57.930 kilo newtons. I think yes.